Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly webinar series. Today's topic is the evolution of insulation resistance testing. My name is Jamie Smith, and I'm the digital marketing specialist for Megger North America, and I'll be acting as a moderator for today's presentation and also supporting you on any technical issues or questions for our presenter. As you can see on the right side of your screen, there's a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment after the webinar ends. All webinar attendees are eligible to receive one NETA CTD or one PDH, and one PDH or 0.1 CEU just for attending. You will receive this in an email within about 2 business days of the webinar. And that email will also include a copy of the PowerPoint presentation and a link to the video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Okay, our presenter today is Jeff Jowett, Megger Senior Application Engineer. Also, to assist with the question and answer session at the end, we will have a panelist joining us by the name of Volney Naranjo, and he's also a Megger Senior Application Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Jeff.
Jamie. Good morning, everyone. We're starting with a timeline here of the accomplishments and the breakthroughs that the company has initiated at various times in its history. We set this against that old browned out photo with the old time equipment to just kind of set a mood for the first part of the presentation, which is going to focus on the development of insulation testers and the evolution of the equipment and how it has improved over the years. So you will see that this goes back to the end of the 19th century, back to the time of the we were still kind of in Industrial Revolution times, and it remained relatively stable for about 75 years or so. This is another look at the timeline and how various innovations were developed and when they came on the market. So you'll see that it remained relatively static for a long time. And the experienced operators in our industry grew up in that type of culture and are familiar with that type of instrumentation, the way it operated, the way you had to use it, and you'll get to see some of those old testers. And then we'll move on to the revolution that began around 1980 or so, and the rapid speed up in development and what that has enabled you now to do. Starting with what was called a ratiometer, one of the very first instruments that was developed, and it used 2 fixed coils, and it was battery powered, and it had a magnetic field. And this type of technology in various adaptations existed for many years and was adapted into a lot of different types of instrumentation, not insulation alone, where you would have fixed coils. And let's see, I think maybe the next slide. Yeah, this gives you a kind of a pictorial look at it. You would have a known circuit with a known resistor in it, and that would be balanced against an unknown circuit that included the resistance that you were trying to measure. And the pointer would be part of the deflecting coil. They were set in a magnetic field at right angles, so they were kind of working in opposition to each other, and the pointer then would strike kind of a happy medium between these opposing fields, and then the measurement would have to be drawn against that. Initially, there was a spring at the base of the pointer that provided the necessary tension to keep it from free floating too much. Years later, that was replaced by what they called a taut band, the idea being to make it a little more rugged and a little more stable. So those of you who are very experienced and have been around a while will probably remember seeing taut band technology and also cross coils, which is what the original technology was called. And I'm sure some of you are familiar with seeing that in old literature, and it's still kind of, to some degree, it's still kind of around today. This was one of our founders, Sidney Evershed. His partner, Vignoles, the original founders of the company in the late 1800s. It was called Evershed and Vignoles, and you still see those letters, EV, they still pop up sometimes. That's where they come from. And if you're looking at very old drawings or very old part numbers and so forth, you sometimes see EV, and that was the origin of it. So they looked at the ratiometer that we just saw described and thought about, well, how do we adapt this to make it more practical for insulation testing? And system pressure, what they're referring to there is voltage, which was extremely important and remains extremely important, and we'll come back to that time and again during this presentation. And so they replaced the battery then and substituted the hand crank generator, which became industry standard for decades and decades. And I'm sure lots of the listeners are familiar with the old hand crank generators, and we still sell them, and you still may be using them. There's really nothing wrong with that. And they initially had the unit in a two-case design. This is a look at one of them, which was the generator part of the unit, where we had the hand crank generator on board. And note the type of technology that went into this: a wood case. Old rosewood cases were very elegant. They remained on the market up until not too terribly long ago. And mechanical operation. Then they put them together in the same box. The first self-contained insulation tester, the moving coils, which I have already described. And here's a look at that old circuitry then, with the hand crank generator serving as the power source. You've got the known circuit with the known resistor. You've got the deflection circuit with a kind of a stabilizing resistor in there, but the main component of that was the insulation under test. And they were working against each other and driving the pointer and reaching a compromise between the two forces that gave you your reading. And at that time, they trademarked the name Megger because it measured into megohms, or millions of ohms, and then that became the general industry name for an insulation tester, but the correct term for it is actually a megometer, but it's so identified with our trademark that it's typically known as a Megger. And here is the old original unit. These were called Meg types. They're still around. They look kind of like old Lionel train transformers. Some of them are still out there operating. I occasionally get calls on them, and I'm sure a lot of you have seen them and are familiar with them. A very nice unit, very easy to operate and carry around, and quite well built. There's a look at the display. And the old units adopts floating position. What that means is until they were energized by the crank, they were purely mechanical, and each one was different in its own little way, and the pointer rest position was characteristic of the specific unit. One unit from another, they would have different rest positions on the pointer. Here's another look at how they were made internally. Note they were pretty labor intensive, not very amenable to mass production, and there were a lot of electromechanicals involved. And the scales had to be hand drawn. And the way they would do this then is each unit individually would be placed across a variety of known resistors, and then the person would mark where the pointer stopped against that particular resistance, and then they would draw the rest of the scale around that. And every individual unit was designed and built in that manner, very labor intensive, rather creative, and each one was quite individual. And as we moved ahead, the Meg types were replaced eventually by what are called major Meggers, and these are still on the market today, very similar to the one we see here. This is one of the original ones. They're not exactly the same, but they're very similar. You'll note, if you can look closely enough at the scale plate on there, that it only read direct at 1 voltage. And to use other voltages, we started to add multi-voltage capabilities. But to use them, you had multipliers or dividers that you had to correct the reading to. And as we go along, we'll see how improvements have eliminated over the years some of these early impediments, or whatever you want to call them, to the full implementation and the correct implementation of these units. This is the old, the British called this the wee Megger in the U.S. market. This was called the midget Megger. And I'm sure a lot of our listeners are very familiar with them, the old Navy men, who are very widespread throughout the electrical industry in technicians and design functions and so forth. And they all trained on these units. They were not much bigger than the palm of your hand. They didn't do very much. A 500-volt tester with a continuity circuit in it, and they only measured up to 100 megohms. They didn't do a lot, but it was enough. And they were very widely used up until fairly recent years, and I'm sure many of you are quite familiar with them. Here's a look at the internals. And again, you can see we're starting to get some PC board activity here, but it's still largely electromechanical. And so for that long period, about 75 years ago, years or so, we note that the instruments were not that much different. There was some little bit of advancement here and there, but nothing tremendous, just a little bit of improvement now and then, like, for instance, the taut band that I already mentioned. And they were typically analog and crank. Then eventually battery power started to come into use, but the initial employment of battery power, not speaking of insulation testers in particular, but in electrical test equipment in general, there were a lot of problems with the old battery-powered units, and one of them is listed there, which would be electrolyte leakage, which would get into the workings of the unit and do a lot of damage. Other things were they didn't last very long, so sometimes to work a fairly intense shift, you had to take several sets of batteries, and if you forgot, then you were in trouble. Another thing that they would do is, as they started to get low, the accuracy of the readings would start to drift. So if you go back to maybe the 50s or 60s, early 70s, there were a number of papers that were written pretty much denouncing battery power. And some of those you might still see around, and if you ever run into an application note like that, take a look at the date on it. Because beginning around the 80s and into the 90s, there was a rapid advancement in battery technology that eliminated all those old problems. But experienced operators still remember them, I'm sure. These are some of the original battery-powered units. And note, we still had the cross-coil mechanisms. Again, they didn't do a whole lot, but note, we're added voltage measurement was built in. So another feature, and we'll touch on that several times, and we'll see why voltage measurement is important. And we started to add more features to these units. And now we're looking at the inception of the electronics. And so that took us into roughly the late 70s, early 80s. That's where the real revolution in the development of these units began. And there's a couple of comments here that sort of cover the important points that began to develop and appear on the market at that time. A point that I'd like to make is that up to about this time, operator involvement was very important in the use of insulation testers, but the operator involvement had mainly to do with operating the equipment properly, getting a good reading, making sure you got the right reading, and not committing errors, things of that nature. Now, the modern units have eliminated most of those problems, and they're very easy to operate, but there is still a considerable requirement for operator involvement, but it's for all the things that you can now do. So there's a lot more capabilities built into the units. And again, the operator wants to familiarize himself with the various features and the different things that can be done and be able to maximize their use. And we'll go and take a look at those. So I guess kind of the final slide in this particular part of the presentation, this is what we now have today, PC board operated units as opposed to the old electromechanicals. And remember, those old units gave you a very good reading. They were good quality units. They were reliable. They just didn't do as much. And they did, as I said, take more operator involvement. So now we'll take a look at the insulation tester itself, what it does, and then we'll go into the various individual features, what they tell you, and how you can kind of maximize their use. The purpose of the tester is to measure insulation. That is to say, the components in electrical equipment that are not current carrying, that are there to retard current and keep it directed in the circuitry and not going to ground, which leads to malfunction, but more importantly, it also represents a danger, a potential danger to the operator. So that's what insulation is doing for you, and you want to be able to test it and measure it and make sure that it's maintaining its maximum capabilities and that your equipment is still, your electrical equipment is still functioning properly and is safe. And note, we now have direct reading. All the old manipulation is gone. You select a test voltage and it's simply a matter of a selector switch position, and you get all the information you need. We measure up into teraohms. I'll talk about that a little bit later. And the bottom point there, the test method is non-destructive. In order to measure insulation, you need a lot of voltage, but you do not need very much power because there is very little current involved in an insulation test. If there's much current passing, that's telling you that it's not insulation anymore. So you don't need very much current to do a good insulation test. Consequently, The testers have a lot of voltage but very little power, and they are non-destructive and they're non-injurious at the same time. They can sting you a little bit, but they can't really, even a 15 kV tester can't actually injure the operator himself. But at the same time, the test item can be dangerous, and we'll come back and we'll talk about that. So these testers are non-destructive. That's a main differentiation from a high pot or a dielectric strength tester, which is more commonly called a high pot. High pots function in very much the same way that an insulation tester does, but they have more power. They're not concerned with measurement. They're concerned with killing the weak, taking something out of service before it can do damage in service. So always, keep that distinction when you're dealing with instrumentation. Keep that distinction in your mind, an insulation tester versus a high pot. So some of the points that are mentioned here, we need a lot of voltage because we need to be able to draw very small amounts of current. We're concerned with leakage current, which is what's getting through the insulation and going to ground or into the operator or whatever, and that's typically very, very small amounts. So you need a considerable voltage to pull that current through the insulation, and you need high sensitivity to be able to measure. We're typically talking now nanoamps here, and a tester needs to be able to measure that accurately, and you need to have a highly stabilized voltage source enabled to be able to do that. These testers are all DC testers. High pots are very frequently AC, but a megameter, an insulation tester, is DC current limited. There's a quick look at one. 2 terminals, 2 leads, in this case going circuitry to ground. The positive terminal, that is not connected to the insulation. Every now and then I get a call of that nature. You do not ever connect to the insulation. You need 2 metal conductors. So that would represent, let's say, if you had a metal jacket on a cable, for instance, you could connect your positive terminal to that. Note that the industry standard is negative to circuitry, positive to the return. And you will see that very often in SOPs. Now, the scope of this particular talk doesn't go into that. You can always contact me and I can explain it in more detail. The main point here is that on modern insulation, that really is not critically important. So if you accidentally do testing all day with the reverse polarity, it's not a problem. Don't worry about it. But when you look at SOPs, especially long-established SOPs, you will constantly see negative to circuitry, positive to return. And that's what we show you here. And then when you energize the tester, you now have a voltage between those 2 terminals, and leakage current is going to travel through the insulation from one terminal to the other. The tester is going to measure that and convert it into the resistance of that particular insulation. And note we have typically the instruments are divided in at the 1 kV level. So for all your building wiring requirements, 120, 240, 480, 600 volt circuits, all of that, all you need is a 1 kV tester. You can then test at around rated, and if you want to do a stress test looking for problems, you can do twice rated. And a 1 kV instrument is fine. Then for like industrial and utility type equipment where you go up to higher voltages, then you jump to a medium voltage rated tester. So fundamentally, your very first determination in buying an insulation tester then will be what is the rated voltage of the equipment that I'm going to be testing, and then select your tester against that. And do you want to do over voltage tests? Think about that. And step voltage tests, we'll talk about that later. For many years, the medium voltage testers jumped to 5 kV. And then in more recent years, higher voltage tests are becoming more and more significant for standards conformances, and also because the insulating materials coming on the market are becoming more and more developed, and higher voltage testing, 10 kV, 15 kV, and so forth, is becoming more prominent. So for many years, if you didn't buy a 1 kV tester, you bought a 5 kV, but now you have more options to go up to higher voltages. The measurement range, the same thing is happening. So think about your testing goals. We're going up to higher and higher measurement capabilities for essentially the same reasons: the development of the market, the development of standards conformances, and the increase in the capabilities of insulating materials. So you want to think about how high do you need to measure and why. And that leads us then to the two basic divisions between test instrumentation capabilities and the goals of testing. There is simple go, no-go testing, where all you need to do is determine whether something is good or bad. This would be like an electrician signing off a job. In those cases, you can buy relatively simple, relatively inexpensive insulation testers that give you enough range. The old, what we call major Meggers, typically went up to about 2 gigohms. Nothing is bad at 2 gigohms. If you have a tester that measures to that range, that's all you need to determine whether something is good or bad. But on the other hand, if you're doing long-term maintenance, electrical maintenance, then you want to have higher numbers to work with. An infinity reading does not really tell you anything other than that you're over the scale of the tester. The thing you're testing is good, but you don't know how good. So if you're doing that type of testing, which would be like long-term maintenance, for instance, would be a good example, then a high-range tester is good to have, and we'll take some further look at that. One of the reasons here would be what we show you on this graph. If you were keeping maintenance records, and note, if you had a tester that only went to 1 or 2 gigohms, you wouldn't be able to construct a graph like this. And this is kind of a distant early warning. What this is telling you in this particular case, that insulation resistance is dropping rather rapidly. And it's still very high, and a single test would make it look, oh, this is good. You wouldn't have any problem with determining whether it's good or bad, but you wouldn't have any idea of the rate of change. And what may be happening here, if this was a motor in an industrial environment, let's say, there could be moisture getting from a nearby process, and all you may need to do is put up some sort of a guard around it, and you could stop this. Okay. And the displays. The old analogs are still around. A lot of people like them. Digital has become the new thing, and that's what is mainly on the market at this point. And there are good and bad sides to both of them. The analogs gave you pointer travel, and your experienced operators were very good at recognizing pointer travel. They wanted to see the pointer traveling up to higher readings, because typically analog units, the pointer rests on the high end, and when you start the test, it pegs low, and then it drifts back up. And those experienced operators were looking for smooth pointer travel. And if they got that, hey, that was good. If the pointer is stuttering, falling back, something like that, there's a problem with the insulation, something's going on, it might be arcing, for instance. So that was the value of pointer travel, and your experienced operators loved to see that. In a lot of cases, that's all they looked at. Digital, on the other hand, when the pointer stops, then you have to figure out what is that actually telling you, because it may stop between lines on the arc. And so it's between the 5 megohm line and the 10 megohm line. So is it 7 megohms? Is it 8 megohms? Whatever. So there was a certain amount of guesswork in that. Now the digitals eliminate all of that. They give you the number dead on, but you don't see pointer travel. So what you can look for then are very sophisticated microelectronic units that have digital displays, but have the capability of analog electronic pointer travel against the logarithmic arc. And so you can find units on the market, obviously ours, that do both. And that gives you the best of both worlds. Accuracy. The main thing here to look at is 2 points. Make sure that the number of digits is included in the accuracy statement. You will see accuracy statements like plus minus 2%, plus minus 2 digits. No digital instrument can fix the last digit on the scale. It will always jump up and down a little bit, but you don't want it jumping up down very much. So make sure that your accuracy statement includes the number of digits, because some manufacturers are relatively, how should we say, poorly designed equipment will omit that because it's not very good. It may be 6 digits. So make sure that you look for that. And then the other thing to avoid is percentage of scale or something like that, because then units that are specified in that manner, the accuracy varies as you go across the scale, because the scales are typically logarithmic. So look for one that gives you the accuracy statement as percent of reading. In other words, it's the same accuracy at all points. So if you have a 2% accuracy, it's 2% at 1 megohm, and it's 2% at 1 gigohm or whatever. So those are the 2 things to look out for on accuracy statements. Now, voltmeters. We pointed a few slides back, we pointed to the voltmeter capability when it was started to be added into insulation testers. For one thing, it's a convenience. It saves you the ability to, having to, if you want to know what the voltage is, you don't have to go get another unit and hook it up. So it's a nice convenience. But far more important is the safety function of a built-in voltmeter. And the old units, if you ever run into some of those old Meg types, for instance, you will actually see sometimes they had a discharge switch on the panel where the operator would then engage a discharge circuit to bleed off the stored charge at the end of a test. Well, suppose he forgets to do that. So we'll talk a little bit about that, because it's extremely important in terms of safety. And if you're ever dealing with new hires, apprentice electricians that are, it's their first day on a job or something like that, always make sure that they know about the discharge function on an insulation tester. First of all, insulation tests are always performed on de-energized equipment, never on live equipment, but equipment can go live for a variety of reasons. And so a good quality tester will warn you at the beginning of the test. It'll beep, it'll flash, it will let the operator know, hey, you're not on a dead circuit here. And that mainly protects the instrument. Years ago, guys would hook up, they wouldn't know what was going on, they would press the test button, and then they would cook the tester. and the repair department would get installation testers back for so-called warranty repair, and they open them up, and there's a burn track across the board from one terminal to the other. That is not warranty repair. You put 5,000 volts or something on this, and we told you not to do that. That has all been eliminated on a good quality tester. Not only will they tell you, but they will also prevent the operator from energizing the tester if there's voltage on the test item. So when you're buying a tester, make sure that it has that capability. Otherwise, you're liable to lose it relatively quickly, like first day on a job. So they will inhibit testing. And the other thing that they do, that's at the beginning of the test or during the process of the test, because sometimes someone will go and throw a switch, which you have turned off but didn't lock out, for instance. But at the end of the test, you also want to de-energize the test item. The tester is not dangerous. The test item can be, because you can store a large static voltage in the construction of the thing that you're testing. A big motor winding, a long run of cable has a lot of capacitance in it. That will charge up, and that will be stored at the end of the test. The operator goes up and tries to disconnect the leads and accidentally gets across the voltage. That can be lethal. A good quality modern tester will automatically begin a discharge circuit and tell the operator that that's happening. So all you have to do is look at the display, and it will tell you what is going on. Okay. And we'll look at a couple more of the functions. Your continuity range. Most of your medium voltage testers don't really need that and don't have that in there, but your 1 kV testers virtually all have a continuity range in there. This is low voltage, low resistance. It's for the opposite side of insulation, which is circuitry. It's a means of telling you that your circuit has been properly connected, there were no wrong connections made at a junction box, and that all your bonds are good. So on a continuity test, you test your circuit, and you want to see an ohm or something like that. And if there's a problem anywhere on the circuit, you get a higher number, and you know that there's an issue that has to be corrected. And the kiloohm range now, again, this is a range that's intermediate between your continuity and your megohms. Here you're measuring in thousands of ohms. And again, this is done at low voltage, usually maybe 3 volts or something thereabouts. And it has some very vital functions. Not all testers have a kiloohm range, but in many cases you want to make sure that you get this. For one thing, it verifies a faulted test item. So you can hook up and run a test, and you run on a megohm scale, and you run off the low end of the scale. There's a fault on there somewhere. Well, it's nice to be able to switch to another range and actually read it and see what it actually is. That gives you something to work against. And it's a very good feature in something like drying out flooded equipment, which in certain parts of the country, of course, and we've been hearing a lot of this in the news over the last few years, that in certain parts of the country, this is huge. Equipment that has been underwater does not necessarily have to be replaced. It can be reconditioned. Drying it out is very important. And you can use your kiloohm range then to see what kind of resistance reading do you get when it's flooded, and then periodically check it as you're drying it out and see that it's becoming effective up until you get into the megohm range. And also, a lot of times components and subassemblies have lower insulation values because they're going to be buried inside a bigger piece of equipment where there is other insulation to protect the operator from ground. So the subassembly only needs to meet performance requirements, and they can be lower. Continuity buzzers, these are a good way of getting in and out of continuity testing quickly by not having to look at the numbers. You can set a buzzer and hear the okay, the buzzer goes off. You made the continuity level and you're good, and you can move on. But a lot of times these things are automatically set, and again, a relatively inexpensive tester may only have one continuity buzzer level set, and it may not be realistic for the type of equipment that you are going to work against. So you can look for testers that have multiple continuity buzzer functions, and that the values that you can set are practical against the equipment that you're going to be working on. And the guard terminal. Some testers have this, some testers don't. It's a shunt circuit. You don't have to use it, but it gives you an extra capability if you do, and we'll talk about that in some degree. It does not stand for ground. If you hook it up as a ground, all you're doing is defeating the purpose of your test. You won't do any damage, but you just won't be getting a valid test. So the guard terminal, you don't have to use it, but whatever you connect to it, it will shunt that leakage around your measurement and will not be part of your measurement. And here's a good example of a guard terminal application on a cable termination. Note that one phase has been connected to the positive terminal. The other phases and the braid have been connected to the return. So now you're measuring that one phase against the rest of the cable. But note that where your alligator clips are, the dirtier or more moist this cable termination is, that provides a good current path. And so you can get surface current tracking across from one alligator clip to the other. That will bring down your reading. That will include more leakage current in your reading, and it will lower your reading. And so you can make a false determination accidentally and think that the insulation is not very good, when in fact it's really not a problem. So if you were to wrap a conductor around the cable termination and run that back to the guard terminal, that leakage would be removed from your measurement. Here's another quick look at a simplified schematic. With the guard terminal, you have two leakage paths in parallel, and you take one of them out. And another good application, again on a bushing, the moisture in the dirt on the bushing can track current from one terminal to the other. Put a bushing guard spring on there, run it back to the guard terminal, and you eliminate that, and you only see what leakage is getting through the ceramic. Okay. And guard terminal performance, this is something you want to look at when you're purchasing a tester. It's the way that tester manufacturers who try to go to market primarily on price, what they will do is emphasize the positive aspects of their product, but de-emphasize or not mention the negative aspects. And one of the areas in which they can save on design costs and manufacturing costs is on a guard terminal. So it takes a good degree of engineering to properly design a guard terminal, because this is a relatively low resistance circuit that is competing with a high resistance circuit, which is your measurement circuit. And it's competing for a limited amount of leakage current. What some manufacturers do is put a high resistance in the guard terminal circuit. This defeats the purpose of having the guard terminal. On the other hand, If you have it at low resistance, now you've got a potentially dangerous path into the instrument for your arc flash protection. So a low guard terminal resistance can defy your arc flash protection, your IEC 1010 protection. So it's a balancing act between these two competing functions to design a good guard terminal. And consequently, you will see products on the market that have a guard terminal error as much as we've seen 80%. And remember, when you add any additional any calibration technician out there knows this. When you put any additional function, there's going to be a certain amount of error associated with that. But what you want to do is minimize that. Our particular products have a 2% guard terminal error, so they're not contributing very much to your reading when they're engaged. But on the other hand, you want to be able to maintain your arc flash. And so always look, arc flash protection, that is. And so always look for that in your specifications. And then data storage and downloading, a very convenient feature. The old days we used to sell test record cards, and then the operators would hang those in jackets on machinery, for instance, and when they tested it, they would put a value in, and they would draw lines between the dots and so forth. And that's how they kept their records. And now this is all done very conveniently, very electronically. And the main function, well, of course, it's very convenient in terms of if you're the online maintenance man and you have to go back to your records to make determinations. But one of its best features is that third bullet there. It eliminates human error, and it prevents a lot of argumentation, especially if you're dealing with third parties, clients, or inspectors or people of that sort who can raise arguments. What do you mean gig ohms? Are you sure this wasn't meg ohms? Well, you got the automatically stored record to prove your point. Okay. And some other things to just take a quick look at. If you noticed, if you remember when we showed those old instruments, ergonomics was not a big factor on those old instruments, but now it certainly is. And ergonomic design can be very important, especially if you're using the same piece of equipment all day long. So you do want to look into that. And things like backlights, locking test buttons, and so forth, take them into consideration because doing something once and doing it several dozen times, like during the course of a work day, can be a big difference. So keep that under consideration. Okay, IP rating. Here's another independent. In the old days, these things didn't exist. And so manufacturers would just make empty verbal claims, rugged, watertight, things like that. And what does that mean? Not necessarily a whole lot. So independence agencies, mostly in the latter part, in the last 20, 25 years or so, have developed where they set independent standards aside. And these aren't done by the manufacturers. These are done by nonprofit organizations like IEC, for instance. And so you can refer to those, and your IP rating gives you the ingress protection or moisture and dirt. How can it get inside of your unit? In the old days, we used to see, especially like in the mining industry, we would get instruments back for repair, and they would be packed with, powder from stone being mined and so forth, or coal dust or something like that, and that would be all over the PC board, and that's the end of the functioning of the unit. So look at your ingress protection. These are a quick look at some of the numbers and what they mean, and just make sure that you match your IP rating to the environment in which you're going to be using your piece of equipment. Okay, load graph. Again, you want to see a very quick, very sharp rise up to the voltage at which you intend to test, and you don't want your voltage to load down at the low end of the insulation spectrum until you get to what is actually not good insulation. So you note this is a good load graph. So this shows you, for instance, that at 5,000 volts, by the time you're up to about 5 kV, which would be the minimum acceptable insulation resistance for a 5,000 volt circuit, you're getting 5,000 volts out of your tester. What you don't want to get is something like this, where it gets there eventually, but over the low end of the resistance scale, and that's where you have to make your most critical determinations, is when the insulation is getting down towards its low end, but is still good, is still operative, but you got to make some decisions. When do I want to test this again, or when do I want to take it out of service and recondition it? And if you have a poorly designed tester with a poor load graph, that is not going to give you valid information. So look for your load graph. Okay. Contact detector, I have to kind of pick up the pace here a little bit. What that mainly tells you is your continuity circuit is low resistance, and so if the fault occurs on your line, and your low resistance continuity circuit is engaged, then there could be a potential shock hazard there. A good quality tester with a contact detector, it will not shift from the input protected insulation range down to the lower resistance continuity measurement range until both leads are connected. The tester knows this, it can sense it. And so you won't have, let's say, a dangling lead or a lead that's connected to metal frame, let's say, while the low resistance continuity range is engaged, in the event that during those few seconds or whatever, some fault occurs on that line. The operator will not be put at any risk. So that's your contact detector. Go, no-go testing, diagnostic testing, we already kind of talked about that. Quickly, this is what happens on your, when you engage an insulation tester. This is your charging circuits. You have capacitive charging, which takes place in the metal of the item you're testing and takes place quickly. You have absorption current, which takes place in the insulating material and takes longer, but they go to zero eventually. And then you have your leakage current, which is what you're trying to measure. So this is why your readings start low and peg high. This is a quick look at the way insulating material will polarize against the voltage gradient, and that's your absorption current that is occurring while the insulating test is going on. And this is why your numbers keep rising as these currents become less and less. So a short time test, the spot reading test, is a very quick test. Note that insulation that is relatively low value but maintaining is pretty confident that it's remaining in good working order, whereas if it's a high value but dropping, that will be something to be more concerned about, even though the numbers are higher. Then you have polarization index. This is a 1 minute reading divided into a 10-minute reading. Oops, let's go back. And the way that works is the operator can make a quick determination without having to resort to interpreting the actual numbers, because the 1 minute reading should be substantially lower than the 10-minute reading, but if there's a lot of leakage current, that holds the test constant, relatively constant, And so you get a low number down around 1. If you got a higher number up above 2, that's telling you there's not a lot of leakage current. It's mostly charging current. So the operator has a confidence factor built right in to the PI. Step voltage, there your values keep dropping each time you increase the test voltage. That is an indication mainly of mechanical failure in the insulation, like it's dropping in voltage each time you increase your value. And let's see, we're getting kind of short on time, so I'll go quickly. Insulation discharge. This is the dielectric discharge test. This is built into some testers. You cannot do this mechanically. You have to do this. It has to be built, or manually is what I was trying to say. This has to be built into the tester. It looks at, rather than the charging currents, it looks at the discharge current and gives you a figure of merit, just like the PI does. And you evaluate your test against the figure of merit. And it's mainly used for multi-layered insulation. So notice your different test procedures tell you different things that you can look for. So your spot reading test, you have to look at a number and make a determination. Your PI is a good test for general pervasive problems like moisture. Your step voltage is a good test for things like localized mechanical damage, brittle, cracked, or pinhole insulation. And your dielectric discharge looks at multi-layer insulation that has a bad layer in between good layers, which can be hard to detect. Okay, guard terminal performance, I pretty much talked about that. I think we pretty much have covered, but the point here was make sure that on your arc flash protection, make sure that it's specified against all terminals, because a cheaply designed tester will give you your IEC arc flash protection against the positive and negative, but it may not specify it against the guard terminal. So you're using the guard terminal, your arc flash protection can go out the window. So make sure that it's specified against all of your terminals. Okay, and with that, we'll take a quick look then at, again, this shows noise immunity, which the S1 series is the best on the market for noise protection. You can look at that. And this is a nice graphic that sort of shows you how you can, on our S1 series, you can engage filters and what those filters do to get rid of noise if you're testing in something like a switch yard. And then finally, you can also get remote control. And this is here you hook up your computer, you program your computer operates the tester. It's a good function to use, especially like around substation testing, which are dangerous for the arcing capabilities. You can get outside of the substation and just have your tester running the tests. And this is your S1 series. These are your medium voltage testers that we offer, a 5, a 10, and a 15 kV unit. And these bullet points pretty much speak for themselves. You get high accuracy in very noisy environments. You get rapid charging because you could be on very large test equipment, has large capacitive loads, and so they can take a while to charge. So that speeds up your testing. You have a very high measurement range up into terohms, thousands of gigohms, which in turn are thousands of megohms. And your noise protection, highest degree of noise protection. You have your remote operation for operator safety. your battery protection, and a couple of the other bullet points there. The dual case design, that is a good safety feature. These testers actually have an inner case and an outer case. And the inner case is designed against arc flash protection, but when casework is designed for arc flash protection, it tends to make it brittle and tend to crack relatively easily. So consequently, we have a second outer case with a different type of plastic for ruggedized applications, so if it gets banged around, it won't crack. So very good protection of the operator for safety and of the equipment for long life. Okay. And finally, I think this is pretty much the last slide. Our 1 kV testers note that the old mechanical analog units are still available. There's a significant segment of the market that loves these units. They're used to working with them. They want to work with that. That's what they're familiar with. That's what they know how to implement the most effectively. We still keep them available. And then we go to the microelectronic units, which are full-featured, and all you have to do, we have relatively inexpensive basic function units like the MIT 200 and 300 series, which if all you need is pass-fail, then that's all you need to buy, and you can save money. But if you're going into demanding and full-featured applications, then you go to the MIT 400 series, the top-of-the-line series, the best handheld 1 kV units on the market. And on any of our data sheets, all you need to do is there's an organization table, and all you need to do is go left to right and see which features do you like, which features do you not need, and you can stop on the specific model that best meets your application. And with that, I am finished this part of the presentation, and we will now go on to your questions.
All right. Thank you, Jeff. At this time, the presentation portion of the webinar is officially concluded. And all right, we're going to now take about 30 minutes to answer as many of your questions as possible. If you have any questions that you haven't submitted already, you can go ahead and submit those now into the Q&A box, and we'll try to get to those if we have enough time. For those that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's also a field where you can request demos or quotes of any of our Megger products, so feel free to do that. Also, a copy of the presentation, along with a link to the video recording of the webinar, will be emailed to everyone within about 2 business days. So early next week, you should receive that. And you could also view recordings of previous webinars and our upcoming webinar schedule on our website at us.megger.com/webinars. All right, we hope to see you again at our next webinar on December 15th at 10 a.m. Central Standard Time. And that one is going to be titled Effect of Different Voltage Waveforms on Partial Discharge Results on Medium Voltage Cables. And that's presented by Jason Sushak, Megger Application Engineer. So I hope to see you guys at that one as well. All right, now let's get to some of your questions. Okay, first question is going to be for Volney, our panelist today. Volney, what criteria is used to determine the test voltage to be applied for a given equipment voltage rating? For example, cables, transformers, etc.
Okay, thank you, Jamie. Well, the very first criteria is to check always with the manufacturer specs and to see what are the recommended practices by the manufacturer. If you don't have access to that, there's other sources to determine the correct voltage to be applied. And One of these sources is the NIDA table 100.1, which is a very useful table. And always, when selecting the voltage, you want never to stress the nominal voltage or go higher than the nominal voltage of the equipment, as Jeff mentioned, so in some of the slides, you can go 2 times, and also there's some specific criteria for other equipment like rotary machines. So it's not a straight answer. You don't want to break down the insulation. You just want to create a current or circulate a current to be able to measure the resistance.
Okay, thank you, Volney. Next question for Volney again. What does the SOP acronym mean?
Well, that, I guess, step of potential, probably it's one of the tests that Jeff mentioned, which is also a useful test to determine if an insulation is in good condition. This is a test in which you increase the voltage every minute and you do 5 steps, and you are expecting to get not a linear, but a constant value of resistance. Resistance should not change with the voltage that you're applying. It should be like a constant result. And if you have a resistance that is decreasing as you increase the voltage, then it's an indication that there might be some partial discharge inside the insulation, and that you might need to take some maintenance actions on that insulation.
Okay, thank you, Volney.
And yeah, I did want to make an addition or a comment on that because I think Volney mentioned that I mentioned that a couple of times in my presentation. There's a lot of them that are around, and if you have to work against an SOP, it might be a good idea if you have a date on it. What happens is organizations write these things, like a particular company might do that, and then to change them sometimes costs a lot of money. And so they're very slow to change them, and they don't always keep up with technology. So it could be that you'll run into an SOP that has recommendations in it that you're saying, oh, why do they want me to do that? Or, it doesn't sound quite right. So if there's a date on it, that helps you a lot in figuring out, oh, yeah, well, the reason such and such isn't mentioned is that didn't even exist when this was written. So you're always welcome to contact me at the office. It's a very common thing that I get questions on them. And so you're always welcome to contact me. I can't overrule an SOP, obviously. That has to come from whoever generated it, but I would be glad to comment on it.
All right, thank you, Jeff. Okay, next question is for Volney again. What would be the minimum acceptable resistance for a wire with 600 volts insulation?
Okay, as Jeff also mentioned, like a go, no-go value will be something below 2 mega ohms is something to investigate. Higher than that, you might let it go and see that and accept it as a pass value. However, if you are trending values, you want to take note of the value and check that the minimum recommended in NIDA value is 100 mega ohms. So that will be like a reference value for a 600 volt equipment, not only a cable, but any other equipment, not including rotating machinery. That has a different table or reference values.
All right, thank you, Volney. Next question is for Jeff. What is the difference between an earth measuring device with a Megger?
Okay, I'd like to thank the person that answered that, asked that question, because that's a great question. I actually typically include that in my presentations on ground testing. Don't try to use an insulation tester. It comes up all the time. One of the reasons is a lot of times they look alike, reasonably. And so if you go to like a tool crib at the beginning of a shift and you're handed your equipment, it's not at all uncommon to be given the wrong tester, and then the guy doesn't really look at it. He goes out to the job and then he's trying to use it and it doesn't work. But it's a great question. Ground testers are at the other end of the resistance spectrum. So insulation is high voltage, high resistance. Ground testing is low voltage, low resistance. You want your ground rod to be as little resistance as possible. If you can get a tenth of an ohm, that's wonderful. Although it's hard to do, but that's the kind of thing you like to see. So for a ground tester, they're on the other end of the scale. They operate differently in the sense that the two circuits, current and insulation, are separate. Obviously, current and voltage, excuse me. In an insulation tester, you've got two leads. So your current and voltage are kind of incorporated into the same circuitry, and the tester just measures it. But on a ground tester, the potential circuit and the current circuit are separated, and they're applied separately to the ground by critically spaced probes. And then you you take your readings and you interpret your results against the position of the voltage probe. And the problem with that is that the current probe has a resistance associated with it. And you're trying to measure the resistance of your ground rod, and you don't. There's no problem because it's not contributing very much. But on a ground, it's critical. So you need to be able to separate your contact resistance associated with the current probe from your measurement. And that's why the voltage probe is separate and can take readings at specific locations. So although they look quite a bit alike, a ground tester and an insulation tester are very different, and you really can't do a ground test with an insulation tester. And especially if someone is giving you equipment at the start of a shift, for instance, make sure that they do give you a ground tester and not an insulation tester.
Okay, thanks, Jeff. Next question is for Volney. For low voltage cables, do both ends of the cable need to be disconnected before measurements, or can we leave one end connected to an open breaker? Connected but not energized.
Okay, so the thing to consider here is that whatever is connected to the other end will be also tested when you are testing the insulation. So if you are interested only in the cable part, you should disconnect the other end. And if you don't care about the particular resort for the cable, but you just want to see if the entire circuit is with good insulation, you can leave it connected, of course, taking care of de-energizing the other end and not running a test in a unsafe place.
All right, thank you, Volney. Next question is for Jeff. Have you or are you aware of test programs that correlate cable insulation aging test results against insulation resistance tests?
Okay. I'm sorry, there was a distraction there. We're looking at test programs that correlate cable insulation aging test results. Are you aware of the test programs that I'm just trying to, I'm sorry, I beg your pardon to the listeners there. I'm just trying to focus that question. I'm just thinking about it a minute. I'm sorry, I beg your pardon. Yeah, that's good. What I can tell you, you might try organizations like IEEE and NETA and so forth, because they try to do things of that nature. And one example that I can think of is that IEEE, their motor testing or rotational equipment testing standard, which is number 43, which I think gets mentioned further down in the questions, that was revamped around the turn of the century, around 2000. And if you look at the introduction or whatever you call it at the beginning of the standard, it actually tells you in there that new insulating materials are kind of rewriting the book. And they actually wanted the data. So they, beginning around 2000, they were requesting anybody to send them data, send them insulation tests, and the type of equipment that was being tested and what the results were and all of that. And they were trying to do something like that. So our own particular company, we don't specifically get involved in that ourselves, because that's the kind of thing that should be spearheaded by nonprofit independent organizations that don't have a stake in it, and then we try to keep pace with them. So if IEEE says we recommend that such and such be done, well, then as a company we try to accommodate that with our instrumentation. And a good example is what I just stated, the IEEE 43. When they reissued that in 2000, they stated in there that they would like to see up to 10 kV insulation testing on equipment that's rated at 12 kV or above. Anything above, they were satisfied or happy with a 10 kV test. So we immediately brought on the market a 10 kV tester. So it's the organizations that actually take the lead in these types of issues, and then a good, conscientious, and quality manufacturer will keep pace with that. And I hope I answered the question, what you were looking for. And if not, you can certainly come back to me and I'll try to elaborate.
All right. Thank you, Jeff. All right, next question is for Volney. What is the place of insulation resistance testing with MB cable? Second part of the question, there are other tests like AC, VLF, tan delta, etc. that seem to be the types of tests to use. Can test results actually tell whether a cable is bad or good?
Okay, so when testing cables, what you need to consider is that cables will represent a very high capacitance, so they can store a lot of energy, and you might not be able to charge that capacitance to determine if your insulation is good or bad. And then that's when you start you need to use another type of equipment for cable testing, and that's why these other tests, as tan delta or very low frequency tests on cables, have been developed for diagnostics. Also for the fault location, you need a lot of energy to be able to create a fault once that you can locate whenever you are trying to find the place of that location. So there's a point where insulation testers would not be able to help you on these activities, and they might be good for whenever you have a very bad situation on a cable that you can need to determine if it's a go, no go, but not for diagnostic or not for cable fault location. For that, definitely you need something else, and we are talking about medium voltage and up.
Okay, thank you, Volney. Next question is for Jeff. For a given insulation resistance of cable, for example, is there a permissible margin that can be applied for pass-fail criteria?
Okay, let me get thought about that. For a given insulation resistance of a cable, is there a permissible margin that can be applied for pass-fail criteria? Okay, very good question. The answer is yes and no. And I'm not trying to be funny there, but what it is basically is it's really a really good core question, because you will see in the literature assigned values. And if you're satisfying yourself, use your own judgment, because if you're a megohm lower, for instance, does that mean that the test item is no good? No. But unfortunately, a lot of times you're going to be working against independent authorities, and what you want to keep in mind is that these assigned values are arbitrary, generally done by something like committee. They're not rigidly scientific. So an example I can cite is the phone companies have settled on 100 megohms for installation of plain, what they call POTS, plain old telephone service. Okay, so if you're the technician who's running these lines, then you've been told they have to be 100 megohms. Now, does that mean that a 99 megohm line or a 95 megohm line is no good? Of course it doesn't. It may work fine for many years, but the company is trying to reduce the number of callbacks, service calls, where something gets installed and then the customer doesn't have satisfactory operation out of it. And they call the company, and it's a costly service call. So they sat around a room full of people at one time or other, and they decided, okay, 100 megohms is a reasonable value, so we'll put that in the spec. So anybody working against that, then yeah, they have to make that. But if you're operating on your own, the more experience you have, the better an operator you are, and you feel free to make your own judgments, because insulation will work fine until it gets down to very low values, and most of these assigned criteria have a very high degree of safety margin built into them. And I hope that answers the question anyway. And like I said before, if not, you're always welcome to get back to me, and I can, elaborate on it more.
Okay, thank you, Jeff. Next question is for Volney. Is the polarization index useful to determine if the insulation of a transformer is good?
Okay, that the polarization index or depends on the material that you are testing being able to be polarized. And when you have oil it doesn't polarize. So the values that you get when you test the transformer are very close to 1. The good thing so that doesn't tell you too much, but the good thing about running a polarization index on a transformer is that there is a lot of contamination. Then you will be able to see that during the test. Your polarization index will be very low. So it can be used, but you have to be careful when using it, because a value close to 1 or not too high above 1 doesn't mean a bad insulation. So that is kind of the precaution to have there.
All right, thank you, Volney. Next question is for Jeff. Can the temperature of the wire you are testing affect the results or measurements that your tester is giving you?
Yes, it can. In fact, it's very profound, and it's one of the most fundamental things you want to take into consideration when you're doing insulation tests. The higher the temperature, the lower the insulating value. And just to give a general idea of magnitude, about a 10 degree centigrade rise will cut insulation values about in half. So it's quite pronounced. And you definitely do, especially if you're keeping records, you do need to include the temperature in any kind of test result. And you can very often correct to a common temperature base. Software can do that for you. So very often you may be working with software or with an instrument that has it built in where you can correct to a temperature base. And you also, anybody else who's going to be looking at these results needs to know that, especially if they're going to try to repeat the test. Because if someone else repeats your test at another time at a radically different temperature, they're going to get a much different result, and they're going to get the wrong conclusions. And another thing in consideration is whether equipment has been operating or not. So if you came in the morning and the facility has been de-energized all night and you tested a motor, for instance, you'll get a pretty high reading most likely. If the motor had been running half of the shift and then you shut it down and immediately do a test, obviously it's going to be warm, and so the reading is going to be decidedly lower. So yes, take temperature into consideration. You can correct to a common temperature base and store records that way, and definitely include in test results the temperature at which the test was taken.
All right, thank you, Jeff. I have another question for you, Jeff. IEEE 43 says that readings above 5G on a motor, generator, etc., are greatly affected by factors other than insulation resistance, and therefore PIs are not recommended as an assessment tool in this case. What are your thoughts on this?
Okay. They picked 5 gigohms. Yes. In general, I would say that was well thought out. We've been hearing that a lot in recent years. Up until, maybe turn of the century or thereabouts, PIs were pretty generally used and pretty generally accepted. But now the capabilities, both the readings of the insulation itself and the capabilities of the testers going much higher. Now we have, guys that are up doing tests in the teraohm range, and they're doing a PI test, and they're getting very low PIs. Well, the reason for that is because by that time, you're measuring so little current that you're not going to see very much of a change, and from 1 minute to 10 minutes, and you're getting a low PI, and people are conditioned to looking at the traditionally accepted PI values and getting the wrong conclusions. And so, like I said on one of the earlier questions, these agencies, standards agencies that are nonprofit, independents, and so forth, they set the trends. They tend to be conservative very much, but a lot of times they're the ones who really, regardless, they're setting the trends and changing the rules. And I think IEEE's on the ball with this. And I would basically, the 5 gigohm value, of course, is like all of these things, is somewhat arbitrary, but it's arbitrary in the right direction. And as a general rule, I would follow that. PIs are very reliable and a very good test when you're down into the megohm range and in the low gigs. But once you get up above that, the number itself becomes so overwhelming in importance that that's what you want to work with.
Okay, thank you, Jeff. All right, looks like we're almost out of time. We're going to go ahead and answer one more. This last one's for Jeff as well. There was no mention of the DAR test, dielectric absorption ratio. Can you speak on that, Jeff?
Yes, no problem. This fits right in with what we've been saying regarding the the radical change in newer insulating materials. Huge polymeric plastics or rubber materials have much different responses to an insulation test than the old materials of, paper insulation and things like that were on the market for nearly a century. So that question fits right in with the whole course of this particular presentation, which is to say that was then and this is now, and we have a lot of adaptation that we need to do, and that fits right in with it. The DAR is like a PI, but with shorter time intervals, 30 seconds into 1 minute or 1 minute into 3 minutes. Those are the new values that are typically being used in DAR testing, because the absorption ratios are becoming, the absorption times are becoming much shorter on these newer insulating materials, and basically that's what accounts for the DAR test. And so especially if you know that if you're working on old equipment that's been around for quite a while, maybe you can stick with a PI. But if you're on newer insulating materials and real high-end stuff and all, go to the DAR test.
All right. Thank you, Jeff. Looks like that's all we have time for today. We had a lot of questions, so a lot of them weren't answered. So we apologize if we didn't get to your question, but we will follow up with you offline, hopefully in the next couple of weeks, to get those questions answered for you. Just want to thank everyone for attending. If you can please remember to answer the survey. That's it. Thank you all again for attending, and have a great weekend.